Welcome back. In our last video, we took a look at mechanical advantage for an inclined plane. In this video, we are going to talk about efficiency. So with our last discussion, we had determined that for an inclined plane with a horizontal length of 5.0 meters, a vertical height of 2.0 meters, and a diagonal length of 5.4 meters, we have a mechanical advantage of 2.7, and that this means that whatever input force we push with as we move a box or some other object up the inclined plane, we will get an output multiplier of 2.7. So in other words, if you have a 5.0 kilogram box, as we do here, which is a weight of 50 newtons, we only have to push with an input force of 18.5 newtons in order to get the box from position A to position B using the inclined plane. That is assuming ideal conditions. That's assuming there's no friction between the box and the inclined plane. That is not possible. In the real world, there's going to be some amount of frictional resistance between the inclined plane and the box, and that's going to dissipate some of our input work in the form of heat. So what we are also interested in for simple machines like an inclined plane, besides the mechanical advantage, is what we call the efficiency, which we use the lowercase Greek letter eta. And efficiency is simply a ratio of the output work, useful work done by the simple machine versus the total input work that we do. And typically this is expressed as a percent. So we multiply by 100. Just to kind of illustrate this process for you. So let's say that we're pushing this box up the incline with some input force. The box is moving against the force of gravity. So the output force is just the weight of the box, mg. We're changing gravitational potential energy. Let's ask the question, what if the input force is equal to 25 newtons? In our last lesson, we solved for 18.5 newtons for our input force under ideal conditions, but if there's some friction between the box and the incline, we're going to have to push with a greater force to overcome that frictional resistance. So let's say that in reality we have an input force of 25 newtons. Well, that now means that our input work, which is the input force times the input distance, would be 25 newtons. That's what we're pushing with, over the diagonal length of the incline, which is 5.4 meters. So that's going to be a total input work of 135 joules, or Newton meters. Okay? Now the output work is going to be the change in gravitational potential energy for the box, delta UG, which is mg delta H. So 5 kilograms times 10 meters per second squared. I'm going to run out of room here. Times 2 meters. mg delta H. We're changing the height, position from A to B by 2 meters. So that comes out to be 100 joules. Barely fit this in here, of output work, right? So if we think about this conceptually, we're actually doing 100 joules of work on the box, but the input force, the pushing force, is really doing 135 joules of total work. So we have to account for that difference. Where does the other 35 joules go? Most likely the majority of that is going to be dissipated as heat due to friction between the box and the incline. But back over to this idea of efficiency, we can set up a ratio of the output work, the 100 joules of work done on the box, to the total input work done by the pushing force, which is 135 joules, and express it as a percentage to get the efficiency of this inclined plane. So that comes out to be 74%. So this piece of information just as valuable as the mechanical advantage when we're talking about simple machines. What is the efficiency? Because you don't want to waste too much energy. So what this value tells us is that about 3/4 of the input work that we do will be actually converted to useful output work on the box. with the other 1/4 being dissipated as other forms of energy, most prominently in the form of heat. So that's one way to think about efficiency, but it's not the only way. We can also think about efficiency in terms of mechanical advantage. So I'm going to erase what we've got here. I'm going to leave the mechanical advantage. We had calculated a mechanical advantage for this incline in our previous lesson of 2.7, but we just worked through an example where we had an input force of 25 newtons. So remember that mechanical advantage, one way that we expressed it in our previous lesson, was as the ratio of output force to input force. And for an inclined plane, the output force was the weight of the object that we were moving, mg. So in this case, 5 kilograms for our box, that gets us 50 newtons of output force. And in our example in this video, we said, what if we push or have to push with a force of 25 newtons to get the box up the incline at constant speed? So if we do 50 over 25, that actually gets us a mechanical advantage of 2 as opposed to 2.7. That's not the same as what we calculated with the ratio of the distances, with the dimensions of the incline. And there's a reason for this. What we're actually finding when we take the ratio of output force to input force is what we call the actual mechanical advantage, which I'm going to label AMA for actual mechanical, oops, forgot my C, advantage. So there's theory, there's practice. The actual mechanical advantage tells us in practice, what do we get? What we calculated up here in our previous lesson is what we call the ideal mechanical advantage, IMA. And that would be the mechanical advantage that you should get in theory under ideal conditions. All right, so back to the concept of efficiency. Another way to think about efficiency is as the ratio of the actual mechanical advantage of a simple machine to the ideal mechanical advantage of a simple machine. So we calculated efficiency with work previously. This time we're going to look at actual mechanical advantage divided by ideal mechanical advantage. And we're going to once again express this as a percent. So we'll multiply by 100. Okay, so we had just calculated an actual mechanical advantage with the ratio, in this case, of the output force to the, the output force to the input force. We got 2 for our actual mechanical advantage. When we took the ratio of the input distance to the output distance, we calculated 2.7 for our ideal mechanical advantage. And if we multiply that by 100, we do get 74%, which is the exact same efficiency that we calculated in the previous case with the output work over input work formula. So either of these ratios, output work to input work or actual mechanical advantage over ideal mechanical advantage, will allow you to calculate the efficiency of a simple machine. All right, so that's a quick run through of mechanical advantage and efficiency. These principles were demonstrated here with an inclined plane, but they could be applied similarly to a lever or a pulley. So you have a basic conceptual background in the area of simple machines. All right, see you next time.